Next problem is fxy is equal to root x into y. Show that this function is continuous at 0, 0. Partial derivative of first order exists at 0, 0 means fx 0, 0 and fy 0, 0 both exist. But fxy is not differentiable at there. It means fxy is not differentiable at 0, 0. So first we will show the function is continuous at 0, 0. So start with epsilon greater than 0 be arbitrary. Consider mod fxy minus 0. Actually this is the proof of the limit fxy as xy tends to 0, 0 is 0. First we will show the function limit of fxy as xy tends to 0, 0 exists and is equal to f of 0, 0, that is 0. Because what is f of 0, 0 is root 0 into 0, that is 0. So let epsilon greater than 0 be arbitrary. Consider mod fxy minus 0 is equal to mod root x into y is mod root x into mod root y is equal to, because mod of a to b is equal to mod a into mod b, and is less than or equal to mod root x. Actually mod x is less than or equal to root x square plus y square, and so this mod root x is less than or equal to root x square plus y square is strictly less than. Actually we can write less than or equal to or strictly less than, don't write this equal to sign, is less than. This is very obvious that value of LHS is root x and the value of RHS is what? If y is 0 then it is x, the value of RHS is x, and root x is always less than x, and if y is not equal to 0 then its right side is also large than root x. So this root x is strictly less than root x square plus y square, root y is strictly less than root x square plus y square. So is equal to, then here write strictly less than, don't write equal to sign, then this into this, and is x square plus y square. Root a into root a is a square. Okay, root a into root a is a. Okay, so this is not 2 times root x square plus y square. There is multiplication. If root x square plus there is root x square plus y square plus root x square plus y square, then it becomes 2 times root x square plus y square. Here is the root x square plus y square plus root x square plus y square, plus if there is sign plus then it's 2 times, because a plus a is 2a, but a into root a into root a is a. Okay, so here is root x square plus y square into root x square plus y square is x square plus y square, and is strictly less than epsilon whenever root x square plus y square, taking root of both sides, is strictly less than root epsilon, and say it is delta. So for every epsilon greater than 0, there exists delta is equal to root epsilon greater than 0, so that mod fxy minus 0 is less than epsilon whenever root x square plus y square is less than delta. And therefore limit of fxy as xy tends to 0, 0 is 0. And f of 0, 0 is 0 by using this definition. F of 0, 0 is root 0 into 0, that is root 0, that is 0. And therefore this limit fxy as xy tends to 0, 0 and f of 0, 0 both are same. And therefore the function fxy is continuous at 0, 0. Now fx 0, 0 is limit h tends to 0, f of h 0 minus f of 0, 0 divided by h by using the definition. And f of h 0 is what? By using this definition, limit the function root h into 0, root h into 0 minus f of 0, 0 is root 0 into 0 divided by, and root h into 0 is 0, or root 0 is 0. So 0 minus 0 by h, that is 0, and limit of 0 is itself 0. And therefore fx 0, 0 exists. Then fy 0, 0 is what? Limit k tends to 0, f of 0 k minus f of 0, 0 divided by k. Write the value of f of 0 k is root 0 into k, and value of f of 0 is root 0 into 0, that is 0 minus 0 by k, and that is 0, and limit of 0 is 0. So fy 0, 0 and fy 0, 0 both exist. Now we have to show this function is not differentiable at 0, 0. Now the first three methods, that is to show the function is not differentiable function, there are 4 methods. Either show the function is not continuous at ab, or show the fx ab does not exist, or show fy ab does not exist. But if these three ways fails, then use the definition and contradiction method. So for this example, the function fxy is continuous at 0, 0. So the first way is not possible. Then fx 0, 0 exists. second way is not possible. Fy00 is 0, therefore third way is not possible. And so we have to show the function is not differentiable at 0, by using definition and contradiction method. That is where we are going to use the fourth method of the function not differentiable at AB. So we assume the function is differentiable at 0. This is the contradiction method. And therefore, by using definition of differentiability, we have f of 0 plus h, comma 0 plus k minus f of 0 expressed in the form h fx 0 plus k fy 0 plus h phi hk plus k psi hk. Just substitute. The function is differentiable at 0, so use this definition. When the function fxy is differentiable at AB, if f of a plus h b plus k minus f of ab expressed in this form, where phi and psi tends to 0, hk tends to 0. Okay, so the function is differentiable at 0, so we have substitute a and b at 0. What do we have? F of 0 plus h, 0 plus k minus f of 0 is h fx 0 plus k fy 0. So here is the function is differentiable at 0, therefore we have f of 0 plus h, 0 plus k minus f of 0 is h fx 0 plus k fy 0 plus h phi hk plus k psi hk. And where phi and psi, limit of phi and psi as hk tends to 0 is 0. Phi and psi tends to 0 as hk tends to 0. Because the function is differentiable at 0, we have this. Okay. So what is f? Then f of 0 plus h, 0 plus k is f of hk minus f of 0, h fx 0 is 0. Here is fx 0 is 0, fy 0 is 0 plus h phi hk plus k psi hk. Then f of hk is root hk by using the definition. F of root k is f of hk is root h into k, and f of 0 is root 0 into 0, that is 0. F of 0 is 0. F of 0 is 0 is equal to, this becomes 0, this becomes 0, h phi hk plus k psi hk. Then put k is equal to h now. Put k is equal to h. Then for we have root h into h, that is root h square in bracket, in root, is equal to h phi h plus h value of k as h psi h. Okay. And so root h square is what? Plus minus h. And take h as common from these two factors. We have phi h plus psi h. And then dividing by h to both sides. So h by h is 1. So plus minus 1 LHS. Phi h plus psi h get cancelled. Taking limit as h tends to 0, limit h tends to 0, plus minus 1 is equal to limit of RHS. And limit of phi and psi are 0 as h tends to 0, because already k is converted to h, and h tends to 0, therefore limit of phi and psi tends to 0. Here is limit of phi and psi is 0 as hk tends to 0. And therefore we have limit of phi h and psi h 0 and 0. And therefore we have plus minus 1 is equal to 0, which is absurd, which is wrong, which is not possible, is impossible, that value of plus 1 or minus 1 is 0. And this is why we have this contradiction or wrong statement. Your assumption is wrong. What is your assumption? That fxy is differentiable at 0, 0. This is wrong means what is correct? That function fxy is not differentiable at 0, 0. This is the fourth way of the proof of the function is not differentiable at 0, 0. So how we can show the function is not differentiable at 0, 0? There are 4 ways. Show the function is not continuous at AB, or show fxy AB does not exist, or show fy AB does not exist, or show use the definition of differentiability and use the contradiction method. That is, this is the fourth way. So if the first 3 way fails for the example, then use the third way. And someone asked the question that if the fourth way also fails, then what do we do? Then if the fourth way is also not possible, fails for the example, then such an example is example of differentiable function. This is the example of differentiable function. So then the function is differentiable. How can show the function is differentiable? Use the definition of the differentiability. Okay, that is, express the f of a plus hb plus k minus f of ab is equal to in the form of the h fx ab plus k fy ab. Use this definition. Use the definition of differentiability. How we can show the function is differentiable? Express this LHS in the form of RHS. Okay. So here is the example of differentiable function. So How we can show the function is differentiable? Use the definition. And how we can show the function is not differentiable? There are four ways to show the function is not differentiable, but there is only one way to show the function is differentiable. And what is that? Use the definition. So show that this function is differentiable at 0 0. So first find f(x 0 0) is limit h tends to 0, f of h 0 minus f of 0 0. So f of h 0, use this definition: h square plus 0 square in bracket sine 1 by root h square plus 0 square minus f of 0 0 is 0. Directly we are given f of 0 0 is 0, divided by h, and this is h square bracket, right, in the bracket, h square into, not plus, into here is into sine 1 by root h square means sine 1 by h divided by h. So h get cancelled. So right here into, not plus sign, here is into sine, h into sine 1 by h, limit h tends to 0, and is 0 because limit of h tends to 0, limit of h is 0, and therefore 0 into this quantity is 0. And similarly fy 0 0, limit k tends to 0, f of 0 k minus f of 0 0 divided by k. Then light f of 0 k, 0 k is what? Substitute x as 0, y as k. So k square sine 1 by root k square means sine 1 by k into sine 1 by k divided by k square into sine 1 by k minus f of 0 0 is 0 divided by k, and it is k into sine 1 by k. As k tends to 0, we have the limit of this factor is 0. So fx 0 0 is 0, fy 0 0 is 0. Now consider LHS. Now we have to show the function is differentiable at 0 0. So when the function is differentiable at 0 0, by using the definition, when the function is differentiable at 0 0, if when the function is differentiable at 0 0, this is the definition. If the function fxy, f of hk, because a and b are 0, so when the function is differentiable at 0 0, yes, fxy is differentiable at 0 0 if f of 0 plus h means f of h, 0 plus k means k, f of hk minus f of 0 0 expressed in the form h fx 0 0 plus k fy 0 0 h phi hk plus k. So consider LHS and show RHS. So consider f of hk minus f of 0 0 and express this in this form. So consider f of hk minus f of hk minus f of 0 0 is equal to f of hk minus f of 0 0 is equal to, what is f of hk? Is h square plus k square sine 1 by root h square plus k square minus f of 0 0 is 0. So divide this in two parts, that is multiply by this bracket. In the bracket we have h square sine 1 by root h square plus k square into sine 1 by root h square plus k square. Then we write this is as h into 0. H into 0 is 0, k into 0 is 0, that is just add 0 two times, plus, right, this is as h in bracket h into sine 1 by root h square plus k square, and write this k square as k into in bracket k sine 1 by root h square plus k square, and this 0 is fx 0 0, this 0 is fy 0 0, and suppose this is phi hk, this bracket, and this is psi hk. Therefore, we have h fx 0 0 plus k fy 0 0 plus h phi hk plus k psi hk. What is f phi hk and psi hk? This is phi hk and this is psi hk as k into sine 1 by h square plus k square. So we will find the limit of phi hk as hk tends to 0 0, and limit of this factor phi hk tends to 0 0 of this, as h is 0, therefore limit of this factor is 0, and similarly limit of psi hk as hk tends to 0 0 0 is 0, and therefore the function is differentiable at 0 0. Why? Because the function f of 0 plus h comma 0 plus k minus f of 0 0 express in the form h fx 0 0 plus k fy 0 0 plus h phi hk plus k psi hk, and where phi and psi tends to 0 as hk tends to 0 0, and therefore the function is differentiable at 0 0. When the function is differentiable at 0 0, again we see the definition. What when the function is differentiable at 0 0, if f of 0 plus h comma 0 plus k minus f of 0 0 expressed in the form h f 0 0 plus k fy 0 0 plus h phi hk plus k psi hk. If we express this is in this form, then we say the function is differentiable. So in order to say the function is differentiable, consider LHS and show RHS. So here is the proof that consider f of 0 plus h, 0 plus k minus f of 0 0, and express it in the form h f x 0 0 plus k fy 0 0 plus h phi hk plus k psi hk, and therefore the function is differentiable at 0. Show that the function is differentiable at 0 0. Another problem. So first find f x 0 0 by using the definition. Limit h tends to 0, f of h 0 minus f of h 0 is this f of 0 0 is 0 divided by h, so it is h square by h, that is h, and limit of h tends to 0 is 0. Similarly fy 0 0 is 0, and consider f of 0 plus h comma 0 plus k minus f of 0 0. Consider this and express this in this form, then we say the function is differentiable at 0 0. So is equal to f of h 0 minus f of 0 0, and f of hk is what? F of hk is what? H raised to 4 plus k raised to 4 by h square plus k square minus f of 0 0 is 0, and then divide this separate in the two form, then h raised to 4 by h square plus k square plus k raised to 4 by h square plus k square, and then h 0 plus 0 k 0, these are the 0, and then plus write this in the form h in bracket h cube by h square plus k square, write this as k into in bracket k cube by h square plus k square, and this 0 is fx 0 0, this 0 is fy 0 0, and h, let it be this is be phi hk, this is psi hk. What is phi hk and psi hk? This is phi hk, this is psi hk, and then find the limit of hk as hk tends to 0 0 phi hk is 0 by k square, that is 0, and limit of psi also, so right here phi and psi tends to 0 as hk tends to 0 0, and therefore the function actually find the limit like this, find the limit first. Now note that limit hk tends to 0 0 phi hk is equal to limit hk tends to 0 0, write that value of phi hk, that h cube divided by h square plus k square, and this is equal to, if substitute directly h is equal to 0, then 0 cube is 0 by 0 square is 0 plus k square, so we have the answer 0 by k square means 0, and therefore it is equal to 0. Similarly limit of psi hk as hk tends to 0 0 is 0, write that part, and then say that fxy is differentiable at 0 0. So this is the sufficient condition for differentiability. Only the statement is important. Proof of the theorem is not included in the syllabus, new syllabus. So just remember the statement. What is the statement? That fx ab and fy ab exist and one of them is continuous at ab, then f is differentiable at ab. So this is the short statement, that fx ab and fy ab both exist, and one of the fx or fy is continuous at ab, then function is differentiable at ab. That is, out of the fx and fy, one of them is continuous at ab, then the function is differentiable at ab. We know that if the function f is continuous at ab, then f is not necessarily differentiable at ab. But if one of them, fx or fy, one of the out of these two, fx or fy, one of them is continuous at ab, then the function is differentiable at ab. So this is the sufficient condition. But we cannot use this sufficient condition in order to show the function is differentiable at the point. How we can show the function is differentiable? Actually, the sufficient conditions are useful to show the functions are differentiable at ab. But we cannot use this sufficient condition to prove the function is differentiable at ab. How we can show the function is differentiable at ab? So this is the proof of the function is differentiable at ab at 0 0. Use the definition of the differentiability. So just remember the statement of this sufficient condition. Okay. So this is about the differentiable function of two variable functions. So the proof of necessary condition, the necessary condition and its proof is important. The statement of the sufficient condition is important, and the problems are also important. So there are two types of problem. The function are not differentiable at the point EB or 0, 0, and the another type is what? The function is differentiable at 0, 0. So I will share you some uh, problems of this type for homework. So solve all the problems of the function not differentiable and the function differentiable. So the next part of the chapter is chain rule. So there are two forms of chain rule. We will see the in the next lecture this theorem, chain rule.